As we said yesterday, today's kind of open-ended. We've got a few things that we kind of think we might do, but really a lot sort of depends upon people here. Certainly for the first, I thought for the first maybe hour and a half or something like that till coffee, we can go over a few things that we didn't take up yesterday, but I'm not exactly sure how to prioritize them. Yeah, then after coffee, we'll yes, hear from you people what your projects are. How many people actually are willing to present? 4. Okay.
Andreas was as well.
It's about, yeah. Okay. Yeah, that's good. Yeah. But,
Somebody else should come, actually.
Yeah. Like 5 stars.
No.
No, I mean, also they want.
okay, so I think that will work out nicely for timing, and then that might continue through lunch or finish just about then, and then in the afternoon concentrate on computing and open source resources and see where we go. So the first thing is, what things would you like to talk about? As far as things that we have, there's the case history on waste dumps, looking at IP. So that's something I think from yesterday would probably be of interest. We have kind of a case history / tutorial with respect to taking multi-geophysics and actually use it for diamond exploration. So that's the context of the problem. But in the end, a major component of that is actually the IP effect that we're able to get. So with airborne data, with time domain data, late time signatures often have negatives. And if you have a coincident loop transmitter receiver, then that's indicative that there must be IP effects. So that was done in the Northwest Territories. There is some indication in some of the ground-based stuff that we might be picking up the IP from the ice, from permafrost. The main IP signals that we see are 2 that are associated, well, they're signals that are associated with a couple of different kinds of rocks. So it actually is a kind of spectral IP. And we were able to put all of that together within the context of generating a geophysical rock model. I showed that very briefly, and then finally getting the, comparing that with the geologic model. Because that also involves IP, and people are interested in IP, that is something. There is we also have something on just extracting EM signal from the IP. We haven't really talked yesterday about like the full signal. When you turn off a time domain waveform, then there's immediately inductive responses that come, and then later on there's an IP response. So the whole thing is actually quite complicated. But I think for anybody here, if people are working on those, perhaps some of the material that I have to show, might just sort of help calibrate things and set things in place. Yeah, lots of stuff on marine EM things, but I think that's not really of super interest.
What type of EM?
Oh, marine.
Marine.
Yeah, with the applications of.
But to me, and what you just said before would be excellent to address that.
Okay. Any other? Anybody else have things, or were there discussion points with stuff that we did yesterday that things weren't clear, or like talk a bit about more? Or? Okay, so let us do.
That is okay, right?
Oh, just a sec, I forgot my. Do you think there's some water outside?
Oh, yeah, sure.
Okay, maybe we'll let's give it a shot. So this was a case history using landfill, about landfill, really trying to delineate the amount of waste, but also to see if we couldn't do the with the spectral IP, try to get some information about different lithologies that are important. So this work is done by Gazzotti et al. 2012, and this is a Danish group. Thanks a lot. So just as background, there was a landfill that was established from, it was filled up in 68 to 78, so 10 years. Approximate surface area, 100 by 100 meters. Most of the stuff was sludge from a waste treatment plant. But there was other municipal waste in there too. And the estimated volume was around 65,000 cubic meters. They, at that time, did not have any containment facilities, so there was no membrane, there was no way to capture the leachate, and there's no sort of isolation system. So this is just dumped there. And the current state is that it's a landfill. They check it out. There's hydrocarbons, there's iron, there's inorganics. And they also know that there is a contaminant plume that's going downstream from here. What we see on this map is an outline. That's where they believe the waste is, sort of the landfill boundary. And then all of these other lines are locations where they've done DC resistivity and IP. And they've also done at these white dots gamma log sensing. So gamma logs are really sensitive to, especially the amount of clay that's there. So they'll use DCIP as well as information about gamma logs. So the general area is that we've got sand and gravel kind of interbedded with clay. So the blues here are sands and gravels. These reds things here are clay, and so you can have water that's in these areas here, and you've got some aquatards. As far as the waste deposit goes, it's probably 6 or 8 meters thick, and there's a clay layer on top that's a couple of meters. The aquifer that they're using for drinking here is currently away from here. It's to the west, and so this contaminant plume is not causing any particular damage at this point. But I think their real concern was that if climate changed a bit and we just had basically an overall increase in the amount of water that was here. And there might be some connectedness that would come through here, and that would cause a problem. So they want to delineate this and see what they're up against. So those are the objectives. There's two of them, actually. The first is, okay, where is the landfill? What's the boundaries? What's the depth? I mean, how much waste can we find? And associated with that, there's this leachate plume that's going through. So you want to delineate that. So that's really the thing that people usually consider when they're talking about landfill problems. But in addition to that, they'd like to identify these lithologies. I mean, maybe these clay layers down here are aquatards, sandy rich clay layers might be still useful from the point of view of potable water, and yeah, there might be some deep silt and clay lenses. So they like to see if they couldn't use the same experiment to delineate what's going on here. Physical properties. The sand and gravel has a very high resistivity, has a low chargeability, and it has a low gamma count. Clays and tills, so have low resistivity, high chargeability, and high gamma. Sands, high resistivity, low chargeability, and low gamma. And the landfill material, probably high, but not 100% certain. Chargeability, be high, and not clear about gamma. So those are the kind of characteristics that you're looking for. And yeah, particularly there's going to be a delineation here about the clays and tills. So this we talked about yesterday. Remember, you turn the transmitter on, and there's initial voltage rise, and then charges accumulate in this induced polarization phenomena to rise up to some asymptote. Turn it off, and then watch things decay. The chargeability could be given. This is one of the ones that I talked about yesterday. So here's the voltage. It's this, just the IP voltage, integrating it over time T1 or Ti to Ti plus 1, and take an average. And here's your value of your chargeability. So this is now in volts per volt, or usually it's millivolts per volt. So that's your chargeability. Here's your DCIP lines, number 11 lines, got the gradient array, 4 seconds on, 4 seconds off, and 25 boreholes, and the gamma logs are in white. So they're going to do an inversion. Yesterday, I presented the inversion that we've been doing for ages, which is just to formulate the problem as being a perturbation problem, and then doing a two-step procedure. First of all, to calculate the conductivity, then use that to calculate the sensitivities. And then that sensitivity operator provided the link between whatever data you've got and pseudo-chargeability. They're doing something different here. They're really working directly with the with a coal representation of the model. I had shown you yesterday what the I don't think I have it.
Just use the good Nelson.
So the real part, so this is steady. The real part as a function of frequency looks like this, and the imaginary part will look like this. So there's many kinds of forms of this curve, but they kind of take the same route. The resistivity at very low frequencies is high, resistivity at very high frequencies is low, and really this difference here between the high and the low part is really reflective of the chargeability. So There's various ways of describing complex connectivity. There's it's kind of a phenomenological way of trying to kind of represent what this is. What they have done and what a number of people have done is use what's called a Cole model. And this is the expression here. So there's a number of parameters. There is rho naught. So that's this resistivity right at zero frequency. And there's m naught, which is the chargeability. That's kind of related to this distance that you have here. There's a tau, which is related to this, where this peak is on the, well, 1 over tau, related to the frequency where that is. And there's C, which is kind of a frequency factor, and really what it will tend to do is to kind of spread out this kind of a curve. C values between 0 and 1, but for a lot of rocks, you know, something like 0.25, maybe 5. But so anyway, there's 4 parameters here that you're going to work with. So now you can imagine that the problem is opened up a little bit, right? Because if you are going to invert this now at each layer, okay, so you're going, here they're just going to do a one-dimensional inversion, and they have a certain number of layers, but each layer has actually got 4 parameters that's associated with it. It's got a rho naught, m naught, tau, and c. So it's a very makes for a very nonlinear problem, and that carries its own challenges, but won't worry about that. They've been able to go ahead and invert this, and again, also kind of use laterally constrained so that things don't vary hugely between, you know, one location and another.
And do you predefine the number of layers?
They did, yes. I think they, why did I think 25? I'm not sure, but yeah, they predefine the number of layers. So if you invert that, if you have a DC resistivity section, you convert it and you can get the resistivity and the chargeability, the time constants, and the frequency dependency. I don't know, what's your methodology here that you tend to use? Do you tend to use more like that kind of 2-step method, or do you tend to just work with the full complex connectivity?
No, more two-step approach, and so most of the data that we kind of collected process is in frequency domain. So that's another difference either. I mean, so there would be afterwards maybe one question to you about spectral content in kind of time domain IT data, because this is actually a lot. I mean, we're talking about time domain data, I think, that are collected here, and there is this. I mean, this frequency domain parameterization of a model. So it comes with the tau and the C and so on, but it's of course also important to look at whether this kind of spectral coverage is actually also controlled by the data, and maybe not only by whatever kind of constraints on the parameters, or maybe partly should be by the parameterization itself, or we don't know whether the parameterization is appropriate. But so that is one reason why we kind of mostly do really two-step approach to kind of first look, okay, what is the spectral behavior that we see, and then kind of think about, is it reasonable to kind of assume a Cole model quantification, phenomenological quantification of the responses, and do we see that, or do we have to pay attention? So actually, more recently, and Maxi will probably present some stuff where he was using that. We also moved on to instead of using this co-code parameterization with one single co-code term to a parameterization based on a relaxation time distribution. Of course, you need regularization then, similar to the smoothing and so on, but it's of course more flexible in terms of representing what you might have. And there might be cases where this is kind of from an a priori point of view already some assumption, which not always you can be, you know, sure about whether that is also an adequate representation. So long answer to you.
No, but it's good. And
so I think it's actually very dangerous to make it even more, or you have to really properly see, okay, is this, like with any parameterization, right? Even like within the imaging, we talked about yesterday a bit about anisotropy, which could be pretty dangerous, assuming isotropic media environments and then having an anisotropic. So always parameterization is a massive a priori kind of assumption that we come up with, and we should also question that.
Right, yeah. So actually that kind of raises an interesting point, because if we're thinking about, you know, inverting for 4 parameters in each cell here, if you think you've got, okay, we've got a number of parameters, so it's C and tau, right? And not, but the point is, if the chargeability of any of these layers, you know, any cell went to something that was really very small, then, you know, the tau and C are, it doesn't matter. They could be anything. It's not going to affect the misfit. So you could just, even things like that should raise a little bit of a warning flag that, you know, things could be, there could be challenges here with respect to sort of dumping everything into one hopper and going. Anyway, so you can do it. It's very valid. Some people do it, and you know, it can work. So after having now done all of these lines here, then they get a chargeability section. So what we're looking at here are 4 lines. You probably can't see them. One is right through here. So they all go right through the waist up. So here's the waist up. Here's 16 that goes through there. I think that's 15 that goes through there, or 11. So we've got a number of sections that are plotted here. So this is what the chargeability looks like. So you've got high chargeability right here, and this coincides nicely with the locations of the boundary. Similarly here, with P11, and then here with P15. So one thing that's certainly consistent is that after having done the IP inversion, that we've got, you know, pretty good localization, horizontal localization of the waist dump. If we then take these results, put them into a 3D volume, and then make an isosurface of 100 millivolts per volt, you kind of confine the waist here, and yeah, use something on the basis of the cutoff is always a bit tricky, because your numbers are going to change. But 100 millivolts per volt is a pretty serious chargeability, and you know, it has a nice definition there. So it might be that for a lot of these waist dump problems, you know, maybe that might be sufficient, but there's a lot of data out here, and it's interesting to see what that can tell you. On on this section in here, let's see where. So now we're going to go out on this line, and we're looking at both the resistivity and the chargeability. So the resistivity is characterized by something like that. So it's very resistive right at the surface, and then there's this very low resistivity layer in here, becomes more resistive, and then it's very low resistivity there. So there's a couple of drill holes on here. There's in particular 1587, which is sitting right in the middle here. So let's kind of follow that through on the very first part. So it starts off very resistive, and then it goes to very low resistivity. So that's what we're seeing here with this layer. At the same time, the gamma log through that hole is given by this black line. And you can see there's an anti-correlation here. So the gamma log goes significantly, increases here. And that already is indicative of, okay, maybe that's a potential clay layer. To add further confirmation to that really complete picture, look at the chargeability. The chargeability is very small, right in the near first few meters, and then there's a large chargeability that's coming in through here. So now if we look as a function of depth, the chargeability increases with depth. So at the same place that the resistivity had that low, and then goes back down. What we've got up here for this layer is that it's a region of low resistivity, high chargeability, and high gamma. So that's very likely a clay. They mention in the text that they're going to regard that particular clay unit as an aquitard. There's water, there's a creek or something that's just simply above there, and fairly confident to identify that's an aquitard. The second layer, sort of a clay-rich sandy layer, is this intermediate layer here between, let's say, 20 and 40 meters. So now if we look at what's happening here on the resistivity, that resistivity is increasing a bit in here, so it's blue, and the chargeability has increased, so it's moderately high chargeability. So this unit in here is identified as being fairly high resistivity, moderate chargeability, and the gamma really high in here. So that's gives them an indication there must be some clay content. The third area we're looking at is right down at the bottom. There's a big conductive unit down here. And this unit also coincides with a high chargeability. Always a little bit to be concerned about when things are just simply right at the edge of the mesh, but presumably they've had a more extended volume that they're actually working with the inversion, and they've used this as a cutoff as to what they think is there. But there is an indication of a high chargeable layer out here, and that coincides with the region of low resistivity. So that's interpreted as silk clay lens, so low resistivity, high chargeability, and again, high gamma. So if you look at the gamma curve, it's gone way up there. The interesting thing about this is that there's a region up here that seems to have low resistivity. If you're going to work with a smooth model inversion, then you're always going to have some, you take a block and the sides are always smooth. So you'd notice that, okay, I've got a high resistivity, or sorry, low resistivity here. If you just had that feature, there might be some kind of a blending that goes through. But this is actually extending fairly high up, so it might be that really is indicating a region of lower resistivity, and it doesn't seem to have much chargeability. That will ultimately be interpreted as perhaps being leachate that's there. And all that's kind of captured in this cartoon geologic interpretation that they've got. So so here's the waste up top here, and then we've got an aquitard here that we've seen. We have this clay-rich sandy layer in here, and then there's a clay lens under here. If there's waste leachant that's coming through, it's interpreted it kind of might come down through here, hit this clay lens, and then move along it. So that's where their interpretation is going to be. If the if you look at the resistivity volume, and you just say, okay, I'm going to take everything that's less than 100 ohm meters and just have that as an isosurface, then what you see is that there's this low resistive tongue that's coming out here. And that's far removed from the waste dump itself. So the waste dump is out here. So there's something very conductive that's coming out here. The potential, well, what this is actually a leachate plume. If you, again, look at a line across here, so that we're on that blue line and move, have different kinds of profiles. Profile 4 is this guy here. So profile 4 is here. Here's the waste dump. Here's profile 4. And if you look at the resistivity, you see there's this major resistivity low here. Put a borehole in there and evaluate what the fluids are, and there's a very high concentration of chlorinated fluids sort of at this depth, sort of about 50 meters depth from the surface. So this plume that we're seeing out here is like the leachate. And that actually happens a lot. At least we've seen that in a number of case histories where you have that scenario, you're continually dumping waste products, especially into some kind of a valley, so you're filling things up. You end up with a lot of waste that is high conductivity and high chargeability, and then outwards away from that, there seems to be a region of high conductivity, but there's no chargeability associated with it. So the leachate itself doesn't really seem to be chargeable, and so this allows you then to interpret this as just being a plume and identifying that. So all of that, I think, fits together really nicely. I think this is a very nice case history. You looked at the DC and the IP, able to get an estimate for the boundaries of this and maybe even the volume, and then from a more fine-grained study to look at some of the features away from the waste and identify some, 3 lithologies that are important, as well as identifying the plume. Yes. So I'm not sure of the. Do you have scenarios here that you've actually seen, waste and then got IP and low resistivity, and then you move away, and you're sort of in a situation like this, you've got some kind of a leachate plume. That's,
well, not really, but we did. But I don't have slides for that case history kind of right now. But actually, also with the colleagues in Aarhus, we did, but that is kind of another landfill area on the island Sante, kind of in the Baltic Sea, small island, and there we did a comparison between frequency domain IP and time domain IP. And
oh yes, yeah.
And then kind of also applying the old kind of processing chain and comparing then results that we got, of course, in terms of chargeability or let's say overall measure of polarizability in whatever kind of terms of whatever parameter in resistivity, but then also with respect to spectral parameters. And that is, I mean, this work is led by the guys in Aarhus, and they work on a manuscript on that. And this was kind of interesting. So basically, maybe to say that here is there were 2 messages. So it was really turning out that it was consistent. The overall results in terms of conductivity and polarization, distribution, and so on. That was, of course, there's been some aspects with different configurations, blah blah blah, different resolution. but it was totally consistent. So although you applied completely different tools from the field to really, the final image.
Yeah.
So, which is always nice to see, because it's not
Yeah.
that often being done, that people really, I remember there's been also in the US at some point, also I think with regard to contaminated site characterization, like sort of test sites where different people came and so on. That was kind of back when they were wondering about the potential of IP also for hydrocarbon or contaminant detection characterization. But that's kind of not that often that you really find that people go there and with a completely different team. So that was really good news also from for us, I think, as we kind of are interested in the methods. But there are certainly then also problems in comparing things at the same level. And that was also what my question was related to on the spectral content within time domain IP data, or let's say transient data. So, so when we looked into those details, it was kind of immediately or very easily turned into something comparing apples with peas. Where it's no longer really consistent, very, very difficult to kind of tell, okay, now what is, and we didn't have that much of ground truth, so we were left with just kind of, two different versions with regard to the spectral parameters. So for instance, the tau, the C, more like the spectral behavior, and so we were discussing things, and you will remember there is papers in the 80s, I think it was really also on the, because within the transient, if you have the square wave response, you have the odd higher harmonics in your response. I mean, from a spectral perspective, but kind of that goes with 1 over n square, kind of if you look at the energy, right?
Yeah, yeah.
I mean, falls off like this. So to which degree? So are you really able, to cover whatever 4 decades of of spectral decades, recover those from a transient measurement?
Right.
So we were ending up in discussions, and of course then it's but that was just also work done with the colleagues in Aarhus. Very interesting, but it's kind of now in preparation and manuscripts.
Okay. Yeah, so it might be, since you only really have power at those like odd harmonics, so you've got a particular frequency for your square wave that's going in. In order to really get good information that you could compare in the frequency domain, you actually might have to do multiple time, square waves, right? So you operate at different frequencies. So I think, a lot of people feel like, oh, I could do just one time domain and I've got all of the frequencies there. But in fact, you really don't, because the power is going off. But if you have at least a couple of these, then you've got a wider frequency band that you're working with, and it still might be more cost effective than actually working in the frequency domain and doing frequency 1, frequency 2, frequency 3, right? So there might be kind of a compromise there where just need to, okay, I'm going to do a time domain, but I need to do it at 2 or 3 different base frequencies to get the spectral information that I want.
And also, I mean, I don't know whether this is the IP field example, right? So maybe it's a good point, maybe also for like just as a comment, all the stuff that's been done that people worked on over the last, let's say, 10, 15 years on the potential of IP, actually through the relaxation time, it's mainly also the magnitude of polarization to estimate hydraulic conductivity or permeability. Because of sensing similar length scales by picking this frequency there or this relaxation and correlating that with a, let's say, hydraulic length scale. Basically all not all of the work, but the more recent work clearly shows that the key part of the response, the important information for this estimation or let's say a correlation between permeability and like the IP property is more in for SIP, it's in high frequency range. So let's say 100 hertz and so on, because it's related to the fine length scales in the rock, when the soils or fine textures, so clay material, silty material, that's small length scales, and that is decisive upon also the hydraulic behavior, right? Whether the fluid could go through or not. So that is actually the key information. The IP is certainly like probably even, you know, above 100. So where it might become very challenging to recover that correctly in the field due to coupling issues, and we might come to that also later on to this problem. And that's why, if this is the case, it can be. This is an issue. Let's put it this way. I mean, the spectral content also in time domain data, so because it's much more efficient to have time domain data acquisition in the field and so on. That's also much more widely being done. There's instruments, I mean, good instruments available, so people do that. But with the, let's say, more standard waveform or injection times, you might actually not get, or it's one issue to check whether you actually have sensitivity with your time domain measurement, also with respect to maybe IP contributions, which are more in 100 hertz range. If you have injected, this was, I think, like 16 seconds for like total period.
Yeah, it was 4 seconds
so
on, 4 off.
You know, so like let's say 100 hertz is already 3 decades or something away from that, right? And then maybe this might be an issue actually. Maybe like you said, I'm fully with that. So I'm only pointing at the fact that if IP is the idea is to use IP for this permeability or whatever hydraulic characterization, then it's due to the texture, just due to the length scales that are hydraulically important. It's probably a relatively high frequency part of the IP signature that we're interested in, while kind of the lower frequency part is, of course, also characteristic of texture, length scales, and so on, but these are hydraulically not controlling whatever the fluid flow, the transport processes.
Oh, okay, that's interesting. Yeah. Is there a good summary paper at this point that would kind of capture like where the state of the art is and some of the things that you've just articulated?
Well, I don't know. Actually. I mean, it's kind of this was just a personal summary of kind of really recent studies and so on. Which one? Well, but that is more like, okay, you can, this would not go into these details with length scale and so on.
I thought the all charged up might be appropriate.
It's in the appendix.
Oh, appendix. Ha. There we go. You know, there might be some kind of a connection that comes in with what I'll show now, because what this might allow it to do is to get back earlier in time and effectively at higher frequencies to pull out IP information. Because the problem, you know, if you're trying to go at higher frequencies or earlier in time, then you might be getting a lot of, or some EM contamination. So possible that, yeah, if you've got really higher frequency IP effects coming in, then this might work. We'll flip through this and kind of stop where things are interesting. So some of this is a repeat from yesterday, so I just can just flip through the slides. Okay. So what we wanted to do here was to kind of give a bit of an overview of how we might separate out the various components of the EM signal, you have kind of a DC part, you've got a frequency part that's due to induction, and you've got some part that is due to induced polarization. And these guys all get kind of mixed up together, and if one can separate them out a little bit more and remove, let's say, some of the EM coupling from the IP portion, then you might be able to sneak back enough in time that get something that is interesting. So here's, if you saw this yesterday, that's basically what we're up against. So here's our coal conductivity, electrode, or membrane kind of polarization, just for understanding how things get charged up, different kinds of, yeah, different kinds of materials. So generally on our overvoltage, we've got something that looks like this, and we go ahead, and this is what we did yesterday, did the inversion in a two-step process, and eventually got a chargeability model, and then we had examples like that. And then for inversion, we saw those yesterday. What we're interested in now is the fact that we actually have EM effects. In other words, if I turn this transmitter off in the DC setting where we don't have any electromagnetic induction effects, I just get a decay curve like that. So that's actually what we showed all of yesterday. However, we also showed yesterday that if I turn the transmitter off, I'm going to get time varying magnetic field, so I'm going to get an effect of that. And what happens here is that I turn this, turn the current off, and I get a response that's actually negative. So this is all an EM induction response. We're going to try to, well, so that's an EM induction response, and then the IP response is actually, so it's still positive up here, it's just this little bit up there. So this is the true IP response. Superimposed upon that is the inductive response, but that's negative. And so the full response will start negative and then maybe kind of go up and then back down. One of the things that motivated us for this was inductive sources, and I'll talk a little bit about that. I'm not sure if you do you look at any airborne data and potential IP from that? It's a bit more challenging, but there's stuff in there, and it's kind of interesting to see what can get pulled out and how useful it can be. So, so these were the two kimberlite pipes that I talked very briefly about yesterday. This is northern Alberta, and this is an airborne system, VTEM system, so coincident loop. And as Peter Weidelt showed in a very classic paper, if you've got a coincident loop system, and so you've got a coincident loop and a time domain survey, there is no way you can get negative responses, even if you have an arbitrary, crazy 3D environment. There's no way you can get 3D responses unless you have chargeability. So this is it's a real diagnostic indicator then, because people fly airborne EM surveys, and invariably there's lots of negative transients. So that means that there are IP effects there. And then the question is, okay, what are these guys? What use are they? It might be that they just turn out to be good clay mappers, but that could in itself be interesting depending on what you're looking for. They could potentially be due to mineralization. Our intrigue was the fact that it might be due to mineralization, and there's two kimberlite pipes that we would like to investigate. The interesting thing about a decay curve that comes over here is that the decay starts positive and then goes negative as an IP signal. But there's a pipe up here that it's just negative all the time. It never ever got to a positive state. And people worried about that for a long time. There's a big kind of effort on the part of the instrumentation companies to see if their instruments were actually working properly, but things gradually got sorted out. They realized, like, okay, no, that's really what it is. There's something up here that's just really chargeable. So I'm going to split this up into two parts. There's a grounded, because we're going to look at the grounded source, and then we're going to look at the inductive source. And I think both of these might be of relevance to what you're doing here. So if we look at Maxwell's equations in the frequency domain, they kind of look like that. Ohm's law is given by this. In the time domain, equations look like this, where Ohm's law in time domain is like that. That is in the absence of any frequency dependence of the conductivity. If we have a frequency dependence, now it's in conductivity, so the shape of those curves gets reversed. So highest frequency is up here, so the conductivity is high, and the lowest frequency is down here. And the chargeability eta is related to the difference in these two divided by sigma infinity. So it's really the magnitude of the difference in the conductivity at really low frequencies and really high frequencies that establishes what that parameter eta is. And here's the co representation in the frequency domain. In the time domain, the response function now looks like this. So if I take this and I Fourier transform it, then I'm going to get sigma of t, and there's going to be a delta function, and then there's this negative response function. So that's an important part of how to think about the conductivity in the time domain. And very often people will talk about, the conductivity as time varying, which can add great confusion, I think, to things. But it's really, this is kind of a response function. And in order to get out our final currents, we're going to have to integrate this with an electric field. So here's how it works if you've got the electrical conductivity is frequency dependent. In frequency domain, there's really no problem working with it. You're working in any individual frequencies, and you just have J is equal to sigma E. In this case, sigma is changing as a function of omega, but you just go in, allow sigma to be a complex number, and just go in and solve it. In time domain, it's a bit more challenging, and one of my students, Dave Marchant, wrote a very nice code for time marching. And in this case, the J in here is equal to sigma convoluted with E of t. So if we have, if I have J is equal to sigma E, if that's the, if that's your Ohm's law, but sigma is frequency dependent, then if you take the inverse transform, then you're going to have that J is sigma convolved with E. And that's what's happening here. So now we have your current density is actually going to depend on what the electric fields were some time ago. And that might make some physical sense too, because remember, everything is kind of dynamic now. The moment that you put an electric field on, okay, then some charges are going to kind of be motivated to kind of polarize. If you leave that electric field on longer, you're going to get more and more. So your currents are going to change as a function of time. So you got to keep track of what the electric field is. So our observed responses then in a situation where we've got EM induction and IP look like this. And this is what I was trying to outline a little bit earlier, the IP response is like that, but superimposed upon that, there's that EM induction response, and so your final curve can go like that. So we're going to define the IP, an IP datum. This will allow us to make a kind of a formulation which we get rid of inductive responses. So we're going to define the IP data as the observation, so this is Maxwell's equations operating on full conductivity, minus what we call the fundamental, which is the solution of Maxwell's equations using a conductivity that does not have any IP effects in it. Right? So this is, and that is effectively sigma at infinite frequency. Okay? So we get a conductivity that has no IP effects in it. We subtract that from the data. Everything left is just going to be IP. So here's a very diagnostic diagram. The response that we're going to measure from our system. I'm changing signs here now so that the response that we ordinarily get just from a conductive half space or something is going to be given by this blue dash line here. Okay, so those are actually, those are positive values. If I have a material that is chargeable, I get this black line here. This goes down, it goes up. And this part here is the IP part. This part up here is really the EM induction part. The red line is the difference. Sorry, I should have said this more. The red line is the difference between the measured and the fundamental. So it's this distance here. So that gives you an IP response that's always positive. But in the first half or the first part of this curve, the IP is very small compared to the EM inductive part. Okay, so that's a couple of orders of magnitude different. At very late time, the EM induction has disappeared, and you're just left with a signal that's coming from the IP. The thing of interest here is this intermediate part where we've got both the EM and the IP completely overlapping. So what we'd eventually like to be able to do is to estimate this fundamental response in this region, subtract it from the observations, and just be left with this red curve here. Okay, so that's kind of our goal. And right now, I mean, basically what people are doing is saying, okay, I'm going to wait long enough so that I just have an IP signal, right? And then just chuck the rest of this stuff. And if, in some cases that might be fine, right? But if you're now, as Andreas says, well, I'm really interested in, the IP signal, the stuff that's happening right up at this time here. So this is 100 milliseconds. So that's 10 hertz. So maybe 100 hertz is up, closer in here. If you're trying to get stuff in there, then there's a lot of contamination going on, and you really can't extract your signal. So here's a synthetic model just to kind of show you what happens. So there's going to be four blocks in here that have various conductivities. So the half space is 0.01 Siemens per meter. So this first one is very conductive. The second one is moderately conductive, so that's 1 Siemens per meter, 0.1 Siemens per meter. That's the same as the background, and this is resistive. And so we'll cut away, we'll have two sections that are through here. The objects A2 and A3, these two guys are chargeable. And we're just going to put C is equal to 1, that's a Debye model. The source wire is in a bit of a horseshoe. So there's an A electrode here and a B electrode here, and the current kind of goes around like that. So we're going to use a single step off and measure in the time range 1 to 600 milliseconds. And I said we're trying to find the chargeability of these guys. By the way, the chargeability of each of these was 0.1, and they had a decay time of a half a second. So if we just look at the DC resistivity value, so like here, I mean, that's a valid DC experiment, right? I just have a generator, I've got a wire, horseshoe wire, and now I could measure the electric fields in a grid across here. So I could do that. I'd get a voltage. You can see the high part of the voltage is corresponding with the current electrodes, and I could convert that to an apparent conductivity, which is like this. So I mean, this is good. So this is your DC resistivity experiment. I got a high conductor here, slightly less there, and it looks like I got a resistor there. So you know, the DC is showing something just in the data. What do we have as you know, with time? So we're going to look at various time decay curves here. So at 5 milliseconds, so A1 is here, so that's our conductive, A2, A3, A4. So A1, which is conductor but not chargeable, has got a response that looks like this. A2 has got this response, and just a sec. Well, let's stick with A1. So here's A1 at 5 milliseconds. It's got this particular value. A2, A3, A4 also have that. If we looked at the broad scale map, what we'd see is that the response functions, when plotted in map form, kind of look like that. So they're really controlled by this high conductivity that's associated with this guy. So as I increase in time, I look at images that are like this. So now, interestingly enough, this second A3 actually has a larger response than this, and here's our block here. So this response here is coming actually from from the chargeability of the object. And now if I go to 130 milliseconds, I'm up here, I see that I've got these two blocks here. So now I'm clearly in the chargeable zone. And at this very late time, I'm definitely chargeable. So, okay, so what are we, there's a lot of stuff happening there. I'm going to go back and take a look at it. So at the early stages, what I'm seeing is a combination of two things. One is the induction in this block, but the other, remember we were talking about the grounded wire, right? And you know what the fields are going to be like from that. So the moment I turn that current off, now I got these fields that are diffusing through. So things are, got this field from the wire as well as induction on the block, and that's causing something then that looks like this. If we look at A2, let's now look at the profiles here. So the recorded value at A2 looks like this. So it's going to start, it's got a polarity reversal here. It goes from dash to red. And here's the fundamental in the blue. And then the difference between those is an IP effect. So at this very early time, the difference here, the IP is really much smaller than the EM induction. So there's really no effect on the response because of, due to the IP. If we go over here, however, we notice that there is starting to be a difference, and that the difference between the fundamental and the observed is starting to be significant. Here's the IP. And then once we get out to this value out here to this time, then the IP is actually the dominant part of that signal. And out here, the IP is certainly way dominant. So things are changing as a function of time. Initially, at early times, we're just seeing the EM responses. At very late time, we just see the IP responses. And in between, we got a little bit of both. So what does that mean from the point of anybody who's working with a time domain EM signal? Is that if you're going to try to recover information about IP, there's an early part here in EM induction, like, forget it. There's just simply no way you can do it. There's a late part out here that there's simply no need to do anything. The EM induction is gone, but there's this intermediate part where maybe we could actually make a difference by taking our, by doing basically the following, taking the observations and then subtracting out what we consider to be the fundamental response. Okay, so that's the procedure. And now the challenge is, okay, I've got to somehow find that conductivity. How am I going to do that? Oh, yeah, sort of just to illustrate how that would work. If we look at 80 milliseconds, here's the observations. Okay, here's the fundamental. Okay, so this is the true fundamental. And if I subtract this from that, then I get this, my IP response. So that's great, right? We have two chargeable bodies. There they are. And when we look back at the observation, we still would have seen these two guys, but there's another whole body out here that looks like may have been chargeable if you interpret that as chargeability. So we don't know the conductivity. We somehow have to see what we're up against there, right? So let's just do something that's simple. Let's first of all just start with a half space. When you're doing ground DCIP, you're doing it in a two-stage process, then sometimes if you just have an approximation to that background conductivity, you can still get out something that's interesting. So that's kind of the motivation here. Maybe we could just take out a half space conductivity and see what we get, and we find that we make a change, but not sufficient. We still have this big chargeable body up here. So how could we estimate sigma infinity? We've got a couple things. One is we've got the DC data. So we could go ahead and invert the DC data. That would give us a conductivity. That conductivity, unfortunately, is contaminated with chargeability because it's at DC, you're looking at something that's fully charged up. So often it doesn't make that much difference, but there is something there to be thought of. But the other thing is that if we come back to our time domain problem, we just said at the early time, these things aren't affected by IP. So I could use early time domain EM data to recover a conductivity. So that's actually what I'm going to do as a 3D inversion methodology, which is basically what we do. So let's first of all invert the DC resistivity. Here's the true conductivity. If we invert the DC resistivity, we get an estimated conductivity model that looks like that. So that's not too bad. It's brought out these two conductors, got a resistor here, and if we did a cross section, we get something that looks like that. Because we've got a gradient array, we only had like one transmitter, right? So we've got just one source, and then we had all these fields. So we're not exciting the bodies from multiple directions. It's more of just a gradient survey, and that really translates back to kind of almost a potential field. So we need to have a depth weighting in that to make, otherwise everything can come right up to the surface. Anyway, it's a bit of a wrinkle. So at 130 milliseconds with the, so we'll use this particular model, do the EM decoupling at 130 milliseconds, and so that's now the thing we're going to subtract. And you see, actually, it's not done a bad job. We still have a little bit of this stuff in here, but we've definitely removed some of the IP contamination just with that. So I think that's a pretty encouraging thing. Certainly much better than the half space. Let's see, where are we here? Okay, so now I'm going to do the time domain inversion using the early time channels. And so I'm using 6 time channels. And here's an example of observed and predicted with one of the particular time channels. And when I do that, I get a sigma infinity that looks like this. So I've actually pulled out the conductivity of this first block really quite nicely, and I've got resistors. So if I do the EM decoupling with that, now I get this as the fundamental. Subtract that from that, and I get this. So this is actually the best result so far. We've got 2 chargeable blocks there, and we pretty much have got rid of this other quantity here, which was a bit of an artifact. So if we do the comparisons of the IP, so the IP data at 80 milliseconds, so here was the true, here was the EM coupling removal with a half space, here was the EM coupling removal with the DC, and here's the EM coupling removal with the time domain EM. So by taking those early times that usually are just thrown away, but actually regarding them as data, inverting them, getting a 3D conductivity, and then using that conductivity as a fundamental for removing the EM coupling, this synthetic shows that's a pretty nice strategy. So that's the inversion workflow that we're actually then going to do. So we've got the IP data, and now we're going to use the linearized form and go ahead and invert for those data. So now so these are the IP responses that we've got. So the true IP bodies look like this. Using the half space, they look like that. The DC resistivity, they look like that. And with the time domain EM, they look like that. So the DC is not done too badly, but by using information that we used to just throw away, we've actually done arguably slightly better. Well, you can't see that on here. That's an isosurface now. So I guess the take home here was that traditionally the early time data have been discarded, but those contain valuable information. We could actually invert them. So what that means is for the collection of the DCIP data, you need just to sample much more finely so that you get these really early times. This I think is
Can I ask a question?
yeah, absolutely.
I mean, you have a description of the time domain and the IP response with time, right?
Mm-hmm.
And that was based here on the COCO parameterization.
Yes.
And so, and you had this kind of sign reversal occur, or basically flipping of the sign. And that's basically controlled by the IP.
Yes.
Effect.
Yeah.
And I guess that actually where it occurs at which times. So here it was like 10 milliseconds or something in the examples. That's directly that is related somehow to the COCO time constant that you assume in the.
Yeah. So the magnitude of the
right.
Of the chart.
So the background of my question is, I think I mentioned that yesterday. Kind of just a couple of weeks ago in August, we collected time domain data in the Alps over kind of an ice body, a glacier, and we've seen actually these negative responses in the, I mean, from the EM perspective, in the time domain EM data,
Mm-hmm.
but those occurred at even earlier, which would be which correspond to a kind of high frequency, so very small, relatively small, or smaller than here, tau, relaxation time. So my question is actually, is it kind of the tau then here for the purpose of the synthetic study, this demonstration, fixed all the time? And second, could you also imagine then that this is because it's, if the tau controls actually where then with respect to time this kind of flipping occurs, do you think that also it could be determined by this type of data? If it's not fixed, or maybe you even determined it and just kind of not showed it?
I think the answer to your previous question is yes. We can actually estimate, well, there's the potential for estimating taus, right, from data and different taus. So I'll show you, that'll come out in an example that we use for the for this TKC, for this diamond kimberlite.
Oh, okay, sorry.
Yeah, no, that's good. Because so what I'm going to do now is to show you an example of, well, I'm going to talk about inductive source IP. So this is really interesting. This really, it's one of these things that once you understand it, you're kind of kicking yourself like, okay, so what's the big deal here, right? But honestly, if in that journey to understanding it, you find yourself kind of going on this Brownian motion path. And the person who deserves a lot of credit for this is Sagi Kang, who is my other co-presenter. And his thesis is going to be on IP. But and we just, honestly, we spent close to 2 years just trying to mess around and try to figure out, okay, how do we really understand this stuff? Because the difference between a control source and an inductive source, in a control source, you're putting current in and you're letting everything build up, okay? Build up to your asymptotic limit, and now you've got a fully charged system, and the electric fields, the background electric field is fixed. There's a lot of simplifications in that. Contrast that with an inductive source in which, at each point, so it's you kind of imagine that, so Andreas has got a particular chargeability and time constant, and in a DC case, there's an electric field that's coming through him, it's constant electric field, things gradually build up, and he's fully charged. In an inductive source, as we saw yesterday, those electromagnetic fields kind of propagate in, okay? And as far as he's concerned, the electric field that he's going to be observing, starts to build up, then maybe it changes direction a little bit, because there's all kinds of things happening, and then it maybe decays down, okay? So the charging up of that cell, okay, of Andreas, is a dynamic system, and it may never reach fully, fully charged, right? You never get that luxury of being in that steady state. You don't necessarily even have an electric field that's pointing in the same direction. Remember yesterday we saw the block with the grounded wire, and in some cases the currents were like vortex currents, right? So if it's a vortex current, that means the electric field is going around like that. That means everything is charging up like in that direction, right? And then a little bit later, you got some other field that's coming in, and so that electric field is coming in a different direction, different magnitude. That's causing other charges to to build up. And you got some stuff that's charging, some stuff that's discharging. I mean, when you think about it, it's a real dynamic mess. Okay. On the other hand, you can just by kind of thinking about who's the big kid on the block and making some assumptions, you can simplify the problem a little bit it still means that you need to understand, at your location, on average, for the full duration of that pulse that's coming through, there will be a time that there's a maximum field in a particular direction. And if you make the assumption that, okay, that field has always been in that direction, that's the dominant direction, and that there's an amplitude that has kind of come up and down, you can actually build in enough information to see what is the kind of polarization state of that. And now, of course, the problem gets really kind of complicated, right? Because I've got a transmitter here, and things are at a particular time, so Lindsay's charging up at some kind of rate, right? And then we'll be discharging. I move along here, and then Andreas is charging up. I'm still charging up Lindsay a little bit too, right? Not so far away, and then gradually get over here to Frederick, and then and yet at the end of the day, you want to have a number. You want to have a chargeability that's associated with each of those cells. So there's a lot of stuff that goes on, and we put together a paper. It was published about 2 years ago. It's in GeoSci, and actually, it's just another thing. I'm just really proud that we've been able to do that, because I think it's the most exhaustive kind of clean presentation of exactly everything, every step that is required to kind of go through and make a bit of a simplified analysis here, so that we could go ahead and invert for inductive source. So that's done, and then I'm going to show you a little bit, sort of generally, what's done. I'm not going to go into any of those details because you need to sit down and look at them carefully. But I am going to take you to a field example over these kimberlite deposits, where we can first of all decouple the data and then invert to get chargeability, pseudo-chargeability at early time and late time. And those two volumes are going to be very different from each other. We're going to effectively regard them as like another physical property. And then we're going to put it all together and get rock types. And also you'll see out of that there will come a distinction between the taus. So there's some very small taus and there's some very large taus. And so you can see that without doing anything in particular, as far as or specifying that you should have these kinds of taus or whatever, they just kind of come out of the analysis. And they do distinguish between two different rocks. So I think there's enough, similarities there with some of the problems that might be worked on here that might find that useful. So let's come back to this place. It's called TKC. It's called Cleat Quai Chow. And there's two diamond pipes. There's one called DO27 and DO18. And I talked a bit yesterday about a diamond. This is kind of a characteristic model of a diamond pipe. So they come up diamond stable at significant depths in the mantle. And when they erupt, they come up quickly enough so that the diamond maintains stability. And then there's a number of different rock units. Ks are all for kimberlites. And generally, because of the eruption, so they erupt out and they kind of blow everything out and then fill back in. But there's often a bit of a lake that's associated with that, and then some sediments. And then there's these different different units. And actually, the one that's really interesting is something called PK, pyroclastic kimberlite. That's the one that has usually the diamonds, at least in this particular case. So it'd be nice to find that. The time domain EM curves, the EM data looked like this. So there's first of all a Dighem survey, So a digem is a frequency domain EM. It's kind of like that resolve. And so this was flown, and was really one of the first indicators that there was some conductivity anomalies here, and that might be associated with a kimberlite pipe. There's an AeroTem system. It's one of the first time domain systems. Interestingly enough, here, this one, the data are all negative. So blue is negative values, red is positive. So those are negative. The VTEM in 2004 also showed that same thing. And then ground nanotem data also had negative transients here. So this was kind of interesting in the sense that we've got a frequency domain and some time domain systems. They all show up the existence of two features, but the time domain systems are all basically negative, both in the air and on the ground. And you can see how that curved on DO18, the curves are completely negative. On DO27 down here, the curve started out as positive, and then we see there is going to be an IP that comes in, and they're going to go up like that. So how do the how does all this work? So here's a sort of synthetic example. We've got a conductive chargeable block that's sitting in here, so it's 60 meters cubed, buried 40 meters, background's 0.1 Siemens per meter, and we're going to now look at how all this works. So what's going to happen is that the primary field's going to generate chargeabilities. They're going to have polarization currents that are going to be built up in a block, and then those are going to subsequently decay. So what are we looking at here? So here's a transmitter loop. Excuse me. Here's a transmitter loop, and then we're going to turn that off. So this is what we were looking at yesterday, right? So we've got a transmitter loop. We turn it off. We've got currents that are induced in the earth, and they're going to subsequently, diffuse in case. So the currents are coming out here, and they're going in there, right? So that's what's happening. A little bit later, so we built up polarization currents in here, and those are now going to be in the opposite direction, and that's what's going to cause the negative transients. So you're building this up. You've got the polarization currents that are there. Then the induction currents disappear, and then you're just left with this. I think. So here's the start. Here's the EM induction. But at the same time, all this is happening, that block is being charged up. And now it's, so we're sitting up over here at this time. So our receiver is directly on top, and you see that the currents are actually going the other way. So those are the polarization currents in the block. Okay, so the thing about that is you just don't get to have any kind of steady state. You've got the same polarization process. So if you think about membrane polarization, these guys don't know from where that electric field comes from, right? So somehow there's just an electric field that's coming on here, and they're like, okay, well, I got to rush this way and move here, and then electric field changes or dies out, and then they go back. So I think putting the two things in context, this polarization, membrane polarization that we talked about, and just kind of visualizing how how that's working when you're putting on a field. And then the next thing is like, oh, well, the field isn't a constant. It's changing as a function of time. You put those two physical concepts together, you got a mental cartoon that kind of understands what's going on. So what's our inversion workflow? It's very similar to what we had before, which was to find that background conductivity, and then we're going to remove the EM responses, linearize the equations, and invert, and then we're going to estimate intrinsic parameters. So we're going to go one step farther here. So the first is the conductivity inversion, which actually presented some challenges because there's part from working with the time domain data, there's parts that don't have any positive values. So what I was talking about before was inverting the early time positive data. They don't exist here. So I need to do something a bit different, but unfortunately we had the DigEm data. So we used a combination of the DigEm plus the time domain EM, kind of cooperative inversion, and we got a conductivity model in plan view looks like that, cross section looks like that. So here's DO18, here's DO27. So that gives us 3D conductivity. And now we're going to decouple. So here's at 130 microseconds. So we take that conductivity, subtract it from the observation. Here's the observations. Here's the fundamental. And watch this one. So when we do our IP data, what we really see is, it used to be this stuff in here, but that's really much more of an EM response. This material up here is much more of an IP response. And now, having done this at 130 microseconds, this is much more reflective of what the IP response is. When we do it at 410 microseconds, so things have changed down here. Notice that so back here at 130 microseconds, everything is positive. Now things have changed, right? So we've got some blues and some reds. So there's some negatives that are coming in here. The fundamental response looks like this. And now we subtract those, and we got that. So that, I think, is just a great example of EM decoupling, right? So this is what you had, okay? If you tried to do some kind of IP analysis on these data, you're not going to go very far. Whereas if you now go to that problem of getting the conductivity, trying to remove it as well as you can, and end up with something like this, now you've got good responses. The next step then is to estimate the pseudo chargeability. So that there's a big leap here because remember I told you about all the complications, multiple transmitters and things moving through in different directions. So there's a big leap in what the previous slide, and actually getting a sensitivity function that's valid for this airborne data, but we're not going to go there. So here is the recovered pseudochargeability at 130 microseconds. You see most of the chargeability is sitting up here at DO18, so it's very good. But there is some that at DO27, there's a concentration of chargeability here. So there's, and some up here. So that's the chargeability, that's the early chargeability. Okay. If we look at later time at 410 microseconds, you see how things have changed. This is dying out somewhat at DO18, and this is very strong in here. So this guy is really kicking in at this time, and we see its big chargeable unit there. If we now, so we could do that. We could do that inversion now. That's done at each time channel. So we had we had time channels in which the EM was contaminating, but by the time you get rid of that contamination, then you look at the number of time channels you have. I think there was 10 or 12 time channels. And now we do a 3D inversion at each time channel, and then for each cell, we've got some estimate of the pseudochargeability at a particular time. And now we take those and we do a parametric inversion to try to find basically eta and tau. C is going to be fixed here. Taking cells in the region of A1 up here and going ahead and finding kind of cold parameters for that, they tend to cluster down in here. Early, time constants of what's that? 10 microseconds. So yeah, between 10 and sort of 50 microseconds, something in here. A2 is, hold on. A1, sorry, this guy here is purple, so they're up here. A2 is yellow, so they're here. A3 is red, so they're down here. So these rocks up here seem to be chargeable with time constants that sort of are in the order of 100 microseconds or less. This region up here where we saw really high chargeability, A4 is all in green, and they lie out here. So those are distinctly different. So those are quite different rock units than these, and arguably even these guys, it's not clear. Maybe there's something that could be popped out of there with respect to saying that they're somewhat different units. So what was the sort of impact on the kimberlite exploration is that we were able to combine various properties of these rocks and generate, first of all, a geophysical rock model, and then got a rock model from drilling, and there was a lot of correspondences. So that's basically it. So both for grounded source and for inductive source, for time domain data, you're going to end up with curves that look like this. Early time might be responsible for just thinking about it in terms of EM induction, which we did yesterday. Late times is IP response, which we did at the end of yesterday, and then that intermediate time that you might be able to fix up a bit. And yeah, so this is what we saw in the grounded sources, in the in the inductive sources. So that was, first of all, to recover the conductivity, and then to compute the fundamentals and remove the fundamental from the IP response to get this, and then invert those for pseudochargeabilities, and then maybe do a next step for looking for cold parameters. So that's it. So anyway, that was, I'm pretty optimistic about using that method for removal of EM effects in IP data, and especially as you're trying to kind of get earlier in time or higher in frequency, you might just be able to kind of squeak in there and see if you can do something. Yeah.
Yeah. So just to get it right, so there's two different chargeabilities. Is that you basically took all of the time channels of your data and then kind of took those as individual IP data sets.
Mm-hmm.
And kind of you went through that overall procedure and kind of these the final result with the kind of two different type of rocks, or maybe then IP mechanisms, maybe related to that different grain size or whatever texture of rock in these two. That was then related to two specific kind of time channels. Was that
No.
the case? No.
No. No. Okay. Okay. So now just imagine you've got 10 time channels.
Yeah.
You're just going to invert each one of them. Right. So, and now you got 10 volumes of pseudo chargeability. Okay. Now you pick a cell, and you've got 10 values of the pseudo chargeability as a function of time. Okay. Now you do a parametric inversion to find out, okay, what values of tau, c, chargeability fit each.
Got it.
And then that just, just like, oh, these guys have really large stuff. These guys have small stuff.
Like a two-step
Yep.
analysis.
Yeah.
Okay. And the kind of the conductivity distribution, like this fundamental EM response, because you were saying at the early times you already had so many negatives, so that was taken from what that was from, nevertheless from early times.
Yeah. So the
because you were also saying that in some cases it was already kind of affected, contaminated by IP and.
Yeah. So here is where, and we haven't done this yet, but we will do it. Earlier on, we were talking about inverting for the full complex conductivity, the sigma, tau, eta, whatever, right? So in our case here, where we had just purely negative values, we certainly can't invert early time, right? So the way to then approach that particular problem is like, okay, we got to start with complex conductivity right to begin with, and make some, see if we can't solve that fully non-linear problem. That's the way that would have to be approached, so that you're actually working with something and you're late enough in time that the numbers that you're getting out are already negative. But so you'd have to somehow estimate starting parameters for these and then carry out that inversion. We were a little bit lucky, fortunate on our case, because we had with frequency domain data. That actually brings up another point. I mean, certainly the frequency domain data are going to have IP effects in them, but because you have this continual on-time values in a frequency domain system, it seemed that it was like we were able to get reasonable conductivities out of the resolved data, even though at those same locations, the time domain data were negative. So there's a few interesting things that happen. Actually, there's a couple of things that sort of like, these are sort of totally by the by on here, but they're really interesting. And that is that there was a diamond rush in Canada in I guess the early 80s, because Canada wasn't known for producing diamonds. And then suddenly they found there was diamonds in Canada. And so people were rushing all over the place to stake whatever they could. It was an absolute frenzy. Anyway, it also meant that places were kind of rushed through without particular due diligence as far as trying to see exactly what's there. And because all in these early stage explorations, all the geologists and guys they just want to find something that's got a good showing, right? And then they put it on the stock market and hype up a big story and get somebody to invest a lot, and then they can walk away with a lot of money if they've done it right, right? So that's kind of a motivation, and in doing that, if they get some kind of a showing or something that looks promising, they'll often overhype it and oversell it, and there it goes. So anyway, there was a lot of that going on. The stock market was just going crazy. But you did have the feeling that it was maybe a bubble that was going to burst. It was, stuff looked really oversold. This TKC project comes on. The owners of that, they found some diamonds. It's a diamondiferous area, and then they decided that they should go and drill a hole and do some samplings. At the end of the day, if they had done a little geophysics, they would have spotted a hole in a very different place. But they spotted this hole someplace that they really shouldn't have, got a pretty bad result out. It had been previously overhyped. And that was a piece of information that when fed into the Vancouver Stock Exchange was the tipping point. And the whole market then just collapsed. So this particular project has got kind of a long history for that. It also had a long history. I think you were gone. I'll just reiterate again. The northern pipe was flown and it had negative transients the earliest time. The geophysicists did not understand how that could possibly be. So they did some people did a couple of things. Like some of them actually just said, "Oh, let's just take the absolute value of these data and just invert them for conductivity," which is crazy. The others said, "Well, look, the instruments are wrong. Let's go back and build new instruments and fly it again." So Aerotem, which did the first one, they built a new Aerotem 2, and that went over, and that got even better results. Then VTEM came along, they flew it, they got better results. So those negatives definitely persist, but that area is now a standard testing site for a lot of companies, just because it's so interesting. Anyway, we should probably go for coffee, and then, so how many people and we can discuss more things later, but I'd like to get going on hearing a bit more from what you people have to offer. So how many people have talks, and if we put a stick around, would you be able to put your talk onto a stick? Okay. Perfect. Yeah, so then we'll just have a coffee, and then we talk about something interesting, like what you guys are doing.
Did you also observe cases where actually the negative transients at later times actually came back?
Yeah.
On the right side. So
Yeah.
Because I mean, from this nice visualization, you could imagine that it was really kind of high frequency. It's very early that then polarization because the mechanism is no longer there. You know, it's kind of away, but still there is kind of induction currents.
Yeah.
You know,
Yeah.
in those regions or whatever, so that the signal then actually.
Yeah. So the double.
Yeah.
Yeah. There's a number of those.
And they had a part yes, that's also yes. And my team took the transfer over on Monday. And then we communicated Friday.
Yeah, it's easy. I don't know my computer.
We recognize the back rows open here from the and then you check what's in the car and what's in the storage room, and then we start. I mean, it was so to say the value of the thing was the car was also expensive. There were also tests that such plastic. So the back door was open, you had two houses directly in front of the city. Yes. I don't know. Yeah. And this. Because this basically some people running actually research center, check all the doors,
Yes, on the glacier, we did some.
and then yeah, I just thought
with my
also for your private.
We still have into it. Okay, now. Okay, good luck. Yeah, this is, well, I don't think it's good because it's approach, but it's not easy.
No, it's not
And it's
easy.
also noise.
Yeah, that's what I
You should go to an area in the world and
Exactly.
we always make it.
I mean, a couple of months, at least at some years so ago, there was also a thing that stole money machines in Mexico. Yeah, actually, I mean, that's something that's also robbery, of course, but there's really money involved. If you steal, it's just these things where all this stuff puts the money into balance the card. I think you steal something like this, which is crazy that it happens. But there is money. But going through research center to steal like 3 screwdrivers and 2 wrenches.
I was also pushing
and
her
I
to
don't know
try
how
to
to
get
call
something
it.
up and running. And they're pushing too much.
Another tool to have some screws that has 6 inches. Also the zero set of this. So it's not really something that you can go exactly. Of course, it's like a 60 or 80.
I also think this is really good about base that side.
Yeah, but I think these
Probably this was from the because it's as soon as somebody
That was so much. No, I mean, there's also different stages. But it's also crazy. Also means this guy or people actually really walk through music centers and check every single door. Every card is
You want to keep yours? We have fresh.
program.
Yeah. That was most part of the day. Central. Almost every transporter also used it. But it still means that every single word on the card and checks. And we also had inside. Provide really professional provide 50 years. So we can also spend it. The teaching started the normal one was 10 years. Yeah. Also Quantenmechanik und dann die Computer der Zukunft, die dann Quantenmechanik, Prozessoren und ich war so alphabetisch geordnet, die Reihenfolge der Präsentation, die war dann noch der letzte.
Aber du dürftest eigentlich auch nicht einfach faul sein, oder?
Ja, und ist dann war manchmal so, manchmal so. Ne? Also dann war ich der Letzte, der präsentiert hat.
Ja, ich auch.
Weil wir hatten das ganz selten.
Dann sitzt man da ja immer so unter Strom so ein bisschen, ne? Und dann höre ich da auch nicht so ganz zu, was die anderen so machen.
Na, letzter ist auch schwierig, dann haben die meisten schon
Ja,
den Favoriten geführt.
ja, genau. Wobei die vorletzte hat auch, war auch ziemlich gut.
Ich denke eigentlich, das müsste ganz gut sein, mal zu so einem Science-Fan zu gehen.
Ja. Also das Template, was ich vorgegeben habe, ich so Drohnenfotos von Pflanzenlust gezeigt, so hellgrün, die Pflanzen geht schlecht und grün, die Pflanzen geht gut, weil da die das Bodenwasser speichern. Das sieht man halt auf dem Boden, Crops, die es sehr gut geht, beschaffen ganz viele Pflanzen, die verdursten. Okay, so läuft so machen. Drillings. Genau, und dann wird man alle so Geophysik.
Erzählt man noch ein bisschen?
Dann sage ich, dass diese Nord-Süd-Nordpolzen GeoPhysics mit
Oder die da hoch.
numerischen Datenanalyse und Kollision und dann gibt es so eine zufällige Modelle raus. Man sieht, dass so mehr als 1 Meter Tiefe in Nord-Süd ist dann der Unterschied ne? Der weiter oben nicht verwandt ist. Und dann gibt es hier noch eine Karte, die Pflanzenaktivität anzeigt. Oder eigentlich ist es Pflanzenwasserindex. Das war richtiger gesagt. Dieses Symbol ist ein Pflanzenwasserindex. Und dann sieht man, dass es den Pflanzen gut geht auf diesen meandernden Strukturen. Ne? Das ist dann dieses Feld hier.
Der auch bei mir anderen schon weg.
Und dann sage ich noch, okay, jetzt gucken wir mal, welche Bodenschicht ist denn jetzt verantwortlich für das Pflanzenwachstum, die Population, Flutlevel, eine mitteltiefere Schicht und dann halt ganz tief. Was dann wahrscheinlich ist. Besserungs- und Nitratanteile optimieren kann, was auch nicht wie besser kommen könnte, auch in geschützt wird.
Wahrscheinlich ist das denen schon hier zu viel irgendwie, weiß ich nicht, Abbildung gewesen, die nicht verstehen oder so.
Es gibt aber viel zu sehen mit der Bewegung.
Ja, ich dachte, ich mag es schon gerne, aber ich dachte auch am Ende, weil wahrscheinlich ist es wirklich weniger viele Bilder. Oder einfach so.
Ich glaube, die Anzahl der Bilder ist gut, aber man weiß halt nicht, wo man jetzt oben Film guckt.
Ja, deswegen kann man das alles nacheinander machen. Das ist wahrscheinlich, aber ja, vielleicht, wenn da wirklich also Schüler und sowas drin saßen, dann ist
Was
nicht so schnell.
für die Motivation, alle sind öfter und Schluss zu setzen. Also,
ruhig auch.
Die Motivation zu einfach das Wichtigste.
Ja.
Schon.
Ja, ich habe gestern gelernt, dass ich in der Schule ist.
Wahrscheinlich irgendwas Diagramm, Zahlen, so auch wirklich. Rechnet dann, nee, also das
Die da gewonnen haben, so Gewinnspiele und sowas, das hat viele Bilder gesammelt.
Ja, doch. Also es war so vorgegeben, dass es alle 2 Folien sein wird und dass auf der ersten Folie so die Motivation gezeigt wird oder das Vorhaben oder auf der zweiten oder die Motivation und auf der zweiten Seite dann noch die Bilder.
die Lösung bereits gelernt.
Do you also have this the like PEM model with the EM responses plus the ILP or is that?
Ich noch was gelernt.
No,
That's not that's not something you can look for responses because you mentioned one quote
yeah,
that was by
Marchant.
March.
Dave
That is
Marchant.
the 2015 paper, right?
Yeah, we're. I mean, those would be the kinds of things that would be nice to have, but yeah, and perhaps we will gradually get them in, but also.
Yeah, although I see the point, it's very specific. So.
Does that stick with
Well, actually having apps in that are specific or learn something. I'll just get the USB back to me that was just loading up his.
Oh, okay.
Computer's passing around.
Yeah, so I'm really interested to know.
This is easier.
Yes.
I'm really used to it.
Just
Show the
so,
you work behind the papers.
Oh, no, Microsoft. That's
yeah, and it's if you just do, it'll get
in my okay, then I run it. Okay.
Yeah. Well, it's sort of, so what's the critical,
I have now a little slide.
Do you mind to describe that?
You want to present forms?
Yeah, no worries. I'll pass it back around. I think it's started.
This is vacancy. So these are the structure, and you see this in frozen state. And this is fence. And it's really, this is the neighborhoods. And the air is it's here that we can actually translate to temperatures, which you can see that basically we're in flowers.
Yeah, so I'll pass this.
Doug, are you good if we get, should we get going again?
Yeah.
Okay. So I'm planning on recording presentations. If anybody would prefer not to be recorded, please just let us know. But it is extremely beneficial for us to be able to look back and have both your slides and the audio of what's gone on, because otherwise we lose track. And it's a really valuable resource to be able to share. So if you're willing, that would be fantastic. But if not, no worries. So I've loaded up the first three. Sorry?
You actually do with the recorded presentation. Is it like published on the web somewhere? Or
Yeah, we'll put it up on YouTube, and so if everybody's game, and then I'll send the links around afterwards so that you can have a copy of it. And then we'll include a short write-up in a blog, and if you're willing, we'll also share your slides there as well. Yes. So who would like to go first? Would you like to go first?
Always send the boss first.
All right.
Establishes the base.
Yeah, actually what I picked here as a short presentation is what was mentioned already kind of yesterday and earlier this morning, that we are interested in using electrical methods for characterization of permafrost sites, where it's basically about, oh, there you go. Where it's basically about distinguishing between kind of unfrozen state and frozen state, and then also if you think of frozen state of a porous rock, basically would frozen mean like completely frozen, all the pores, or kind of only parts of the rocks. And we had the idea of also using induced polarization, and that was motivated by some earlier work. And here's kind of a quick summary. I mean, resistivity, DC resistivity, or ERT, is used now by a number of groups in for permafrost site characterizations. So this is one example actually that we did in collaboration with colleagues in France, in Chambéry. Actually, this shows the Aiguille du Midi, like almost 4,000 meters high granite peak, where this is kind of a resistivity image that was computed based on data that were collected. You see here the black dots, that's the electrodes, and actually kind of really alpine specialists helped us with the installation and so on, but it's kind of a real image. And that's what resistivity is used as a kind of valuable indicator for thermal state. And for instance, here you see, so this is kind of less, it's still kind of resistive, but it's less resistive than kind of the red parts. So red here now indicating kind of high resistivity, and basically what you see here is then the warmer temperatures associated with lower resistivities and then diffusing into the rock then in summer. And actually also these diffusion times of like describing the thermal conduction mainly, that's kind of order of a couple of months. So basically when kind of interpreting actually those high resistivities, you probably see kind of the winter signature from 6 months before within the rock. And so that's a valuable information, DC resistivity.
So
and
that number of 10 to 7 millimeters, that's expected? It seems really big.
Well expected. I mean, they, not we, but there's been some measurements on samples also from the side, and it is not that resistive, but it's actually not unexpected. So it's much more resistive than, I mean, if you look at this is resistivity versus temperature for, this is from an old, I think this is the early 3-volume book by SEG, Environmental Engineering, Geophysics or something, and there already is this kind of chapter, a nice chapter in it on the use of geophysics for permafrost characterization. And and if you look at this, so people are well aware of the fact that resistivity can be used as an indicator for kind of thermal state or for kind of temperature here, and you see basically the increase of resistivity, and it could actually come up to, well, 4, 5, 6. So what we've just seen is even more than that. So I see your point, but basically, so that's interpreted or understood as, okay, as soon as the liquid water with whatever ions as charge carriers is frozen, is gone, okay, no longer pathways are provided for current, and so this makes it resistive. So it's a nice thing to use that, but the question might be, okay, if you measure one value here, to actually go back, because this curve for gravel might be slightly with different porosity, different pores connectivity might be shifted, and so to go back from a particular value here and to kind of discriminate frozen from unfrozen is kind of challenging and sometimes not doable. And that's why we thought of actually using induced polarization, and we've seen that yesterday a little bit. So other than in the examples that we've seen that were based on chargeability as kind of the descriptive IP parameter, we measure and also do modeling and inversion of IP in the frequency domain based on some complex conductivity, where basically the IP information is then captured in an imaginary component of this complex conductivity, or of course also then reflected in the phase of this complex number. Okay, and if you look now at, and this is also well-known stuff, at the polarization again, here shown in terms of electric permittivity, real and imaginary components of this, then you have the polarization, well known, of liquid water here, right here. So basically describing then the molecular polarization, orientational polarization of the water molecules, right? In that frequency range, so where we have the GPR then working, and actually, so this is a polarization mechanism provided by the medium, so by the liquid water. But if you look at ice, it's also well known that there is also a polarization mechanism provided, which is associated to defects of the crystal lattice, and by that kind of deficiency of charges within the crystal lattice of the ice. And it's also, there's different types of ice, which is to some degree able to be kind of locally separated, so moved around. So it's a polarization process which is completely different from like the membrane polarization or the electrode polarization. Yeah, like that comes with the ice. And if you look where this kind of occurs, that is a much lower frequency than, because you like the liquid water polarization, and it falls into the range actually, which is also covered to some degree by IP measurements, at least high frequency, let's say, induced polarization measurements. It's certainly also in the kind of range that where some of the EM induction methods kind of work. So, and so there's no, there's a reference here, but there is a number of papers on kind of this phenomenon. Also, it comes with a nice, relatively sharp cold-cold response, this kind of mechanism. And so can we use that in as a signature that we measure through IP, or maybe also through EM with IP and so on, but which is indicative for not only the presence of ice, but where we might perhaps even use then the kind of magnitude of this polarization in the frequency range as an estimator for, let's say, volumetric ice content or something. And that would be a major step forward compared to kind of the problems associated with the quantification and detection of ice based on DC resistivity alone, because it's much more ambiguous. And just to kind of start with, and that's kind of now the final slide, we first looked at the response in the lab with lab measurements in this frequency range using a standard 4 electrode setup with cylindrically shaped current electrodes, and used sandstones and actually 1 limestone. So really these rock samples with different pore size distributions. And and basically put them in a climate chamber, small chamber, and started kind of in unfrozen state somewhere here. You see here temperature in degrees Celsius, 4 degrees, and then basically kind of expose the sample to lower temperatures. And we did that not dynamically. That's also what we did, but in the end we kind of used small temperature increments and actually waited about 4 hours. So we did some calculations on the thermal equilibrium, so how fast would the thermal conduction, the propagation of the thermal signature into the sample be, and so on, to basically kind of assume that we have more or less a consistent thermal state of the whole sample. So that's why actually all this circle, what you see here now is kind of a freezing, and then this thawing, like every dot you see is basically like we waited 4 hours and then kind of run these SIP measurements. Or basically we run them also before, but this is what you've shown, kind of the sort of thermal equilibrium. And kind of interestingly, this is now resistivity. So this is the standard information, and it's also interesting because it shows, of course, this resistivity increase. And what you see here, this hysteresis that we have, is related to, it's also documented in the literature and well known, and this is related to phenomenon of supercooling. So although the melting point, let's say freezing point, is already kind of past, it still keeps this, the water is in the liquid state, but in the supercooled state. So where then it's just waiting for sort of a nucleation trigger, which is kind of also something that is discussed and investigated what is actually is, but normally it starts then in porous system in some corners or whatever. You might have seen movies where also a mechanical trigger is enough to immediately then kind of turn it from liquid state into kind of crystal state. And that's then, this is really a tipping point for the system in terms of its state. And once that occurs, poof, we have this resistivity increase because the conduction pathway is lost in the sample. And then we have, okay, some increasing increase which continues with lower temperatures. And when we come back, we do not observe the supercooling, but what we do observe is actually successive melting of the pores of the rock, with first kind of the small pores melting first. And this is also well known that basically we have a melting point depression which is related directly to the curvature of, let's say, the spherical water droplets and the other way around. So basically this means that large pores freeze first, or in other words, coming from low temperatures, small pores melt first. right? So we have here certainly already some amount of liquid water in the sample, but in the small pores. And as kind of we now approach again here 0 degrees, we have more and more pores, and also the larger pores then again becoming liquid and contributing to the then conductivity here in the unfrozen state. Anyway, that's a long story, and I guess I have to come to the, this effect, this phenomenon is referred to as Gibbs-Thompson effect, this melting point depression related to this curvature in porous systems. So when you say like this rock is frozen or soil is frozen, that doesn't mean that kind of it does not contain liquid water, right? So that you have to keep that in mind when, in this context. And now this is the IP data, and that's kind of, we find it promising to continue with also trying to measure IP really on-site in the field using this method. This is now for one of the samples, the sandstone. You see here the resistivity, and you see here the phase. So this as a measure of the polarization versus frequency. Here again, just for kind of an overview of the whole thermal cycle, the resistivity as a function of temperature in this freeze-thaw cycle. And this is kind of a typical SIP response that we know also for sandstone. So we have sort of a measurable, and actually that's already kind of pretty solid polarization signal or magnitude in this lower frequency range, and that then kind of fades away as with increasing frequency. So, and these red curves, there's more of them. That is actually already the different spectra measured on the way here when actually freezing the sample. So these are in red, and if I now continue, maybe I should say that. This is what people for sandstones associate with some membrane polarization, so pore space related mechanism, as Doug was describing earlier. So this is kind of the mechanism behind that, where then also people, by for instance quantifying the position of peaks and so on, so quantifying the relaxation times, try to estimate hydraulic length scales and so on of this porous system. And now this is what happens if we kind of look at the freezing curve. Once we come to that tipping point, that we see that here, basically both jumps up, that is the resistivity, and then with kind of the lower the temperature, the more resistive the sample becomes. So that is the resistivity spectra, resistivity magnitude spectra, and the phase. You see two things. One is that at high frequency, I mean, there is noise here, considerable noise actually on the sample. Of course, there's issues with such a resistive sample to coupling and all this, but nevertheless, it's very systematic what you see here, that you get in whatever this is, this signature here, which systematically shifts to even larger values and a bit to smaller frequencies as the temperature decreases. And at the same time, so this is one thing, and the other change, if you compare those blue spectra with the red spectra, is that you lose this contribution, basically, frequencies. And so our working hypothesis is, and I mean, it's kind of relatively straightforward, because if you look, if you would fit cold models through these kind of spectra, those time constants would actually also be in agreement with what you know, where the time constant, where you would expect the time constant from ice. So it's kind of relatively obvious to, as a working hypothesis, to assume that this is the signature of ice, directly polarization signature. Although we might have, problems also with contamination of EM effects, capacitive coupling, and so on. But it's very systematic, and at the same time, we lose this polarization in the low frequencies, which is related to this membrane polarization, so to ion migration, ion diffusion, and this interaction in the pore space. But as soon as maybe an obvious part of the pore space is frozen, okay, there is no longer the space for this mechanism. So it's also kind of very plausible to explanation that just kind of this mechanism breaks down upon freezing of the sample, and we get this high frequency response here. And yeah, and this is like I was saying, so you can fit that reasonably well with Cocold phenomenological model and extract relaxation times, and then kind of compare that with literature values. And yeah, and so the idea is here you see again, this is just the thawing, which basically shows you, okay, it comes back to this original state, but it doesn't show this jump here, this supercooling phenomenon that you have on the freezing path with this abrupt change here. You don't have that on the thawing side. And all this behavior is also, oh no, that's it. That we found that also for other samples, and the hysteresis was even, and the kind of significance of the jump even larger for this limestone, which comes with much smaller pore sizes that we know from the pore size distribution. So of course this then, with the idea of this Gibbs-Thompson effect, the broader the pore size distribution, the broader the stronger this hysteresis. That's what we also observed. And so with this, basically, we now, this is old measurements, actually. Maxi conducted those in the Zugspitze, this ice mountain in Germany. There is a tunnel where we kind of started trying to measure those responses, also systematically compared kind of frozen, unfrozen areas to measure that also in the field, with the ultimate goal of maybe doing that even in an imaging framework. So applying, as an example, IP together with resistivity as an imaging tool for, let's say, thermal state characterization, and maybe even ice content quantification, or let's say estimation in permafrost environments. So that was the example that I'd like to share with you. And yeah.
So do you have a simple explanation for how you see the polarization of ice happening? You talked about some kind of dislocation mechanism.
No, I have nothing, no understanding of that, or no model of that goes kind of, beyond that simple idea that we have just kind of, okay, judges that are somehow. So I myself, I didn't look into the kind of, solid state physics of these things, and yeah.
But it's sort of with the defects in the ice, did you say? Or?
Yeah. So it's kind of characteristic. It's a crystal characteristic, and if you look, I don't remember the number. Maybe Steffi, you remember how many different types of ice do they kind of classify? And it was like 10 or.
You mean the crystal?
Yeah.
The Arten?
Yeah.
Yeah, I think a little bit less than 10.
Or maybe 7 or 8.
Yeah, something
kind
like
of different ways depending on the on different kind of temperature, pressure, the kind of conditions when the crystal forms. So, and that is, so I would not be surprised if this is also related to then some of the kind of polarization effects that comes up with that, or is associated with that kind of crystal characteristics that you have.
So would like a characteristic tau for ice be something then in the order of like 10 to the minus 5 seconds?
Yeah.
Because you had some curves.
Yeah.
I think you went to 10 to the 4 hertz and things were still climbing. Yeah.
Yeah, but it is. There is thermodynamic models which kind of describe this temperature dependence of things, and I mean it depends on actually now the temperature range. So yeah, you can you can basically imagine, okay, as lower the temperature, the more kind of the more moves this signature to lower frequencies. So basically, it covers like several orders of tau. right? So this response kind of starts here at 10 kilohertz maybe, and then yeah, there is, I mean, it's not seen here, but there is kind of also a tau variation in that, which is expected from the, yeah, which is basically shown here in this, by the way, a very old work by one of the Cole brothers himself. Who was so this is how you kind of sometimes realize, okay, they did that too, or in 52, yeah.
So have you worked on any ground-based systems on permafrost? Because under those conditions, I know when they tried to go up and do time domain EM surveys, that they have real challenges in permafrost areas sometimes.
Yeah.
I just realized, like, okay, that's probably ice, but yeah, and then they charge it in order to try to, let's see how to go. Yeah, so in order to try to find like a coal model that would reproduce those responses, the chargeabilities were huge, like 0.9, 0.95 or something. And I don't know, I'm just wondering, does that kind of fit with any of the stuff that you're doing?
Well, we have no, to this point, no experience ourselves with EM measurements, but like I was saying over coffee before or over beer last night, I don't remember. We
and it was clearly the beer.
Yeah, it was. Yeah, we tried it this summer together with a colleague, Adrian Flores Orozco from Technical University of Vienna, and did some TEM soundings with a check device it was, and that's why I'm asking before on kind of your studies that you presented, because that's what we observed. I mean, already in the field on the very kind of, poor visualization and on the laptop and so on, these kind of reversals. And I remember that why I asked that also the polarity changing again. So somehow, which would mean from what you just taught us that basically then, okay, IP is gone, but EM is still there. And maybe that is actually related. So we pick different places in also close to one of the sites that we are now increasingly working on in the Alps together with colleagues in Fribourg, that is in the close to Bern or not too far from Bern, 1 hour or so in the. And there we actually went up to one place which is 4,000 meters almost, where we have a glacier. So where we have ice, really several meters of ice directly kind of below us, and compared those responses with the device with other places. So we went up to, and it was systematic. So that was kind of first trials. But I guess there is people who are really kind of in the EM community who have much more experience and maybe tried these things out. But at least, so I also started looking again in the literature, but I know that at least in the permafrost community, there is no awareness for kind of EM induction methods, and that there might be a signal even in there that is related to ice. So I find it a kind of, not only kind of scientifically exciting point, but it might also be, like you're saying with the disk, maybe, by communicating with those people, maybe there is something that could help to, to come up with such monitoring data, which is for them very important to calibrate their models, their process models, their hydro-mechanical process models, then often related to mechanical stability of rock slopes and all this kind of stuff. Right?
Yeah. Oh, nice.
Okay. Yeah.
Are there any other questions? Who would like to go next?
I can do it, but I have a new PDF.
Sorry?
I have a new PDF.
Okay. Would you mind putting it on the stick so that we can use, just so that we can capture it? One question I had while we're waiting this up. Here, there's a much bigger spread between this side and this one. And is that related to the hysteresis?
Yeah.
Yeah.
So on the freezing path, it just kind of jumps up immediately, and that's why we, with the same kind of temperature increments,
Yep.
it's kind of more distributed even in the form case.
Okay.
In the lower case.
Huh. Thanks. Oops. Which one is it? This one?
The first one, yes.
Can you also copy and paste the other presentation?
Oh, yes, sure. We can.
Okay, if the old one is still usable, then I can use this too. Perhaps anybody else while I fix my PDF?
No? Would somebody else like to come up while he gets his PDF sorted? Who's the other one? Okay. Is it ready to go? Yeah. Do you mind if we... We'll give it a sec. We'll try. We'll give it one more try. Are you on the Slack channel? Because you can also... Okay, that's fine. Okay, I'll give that a try. Yeah. Sorry, the computer's not recognizing it. Let's try it here.
None of the presentation is kind of right. I have to correct everything.
Like, yeah, now that you're trying to better work. Screw all the technologies, kind of screw out equations, try. Okay, that one seems to be working.
One sec. Sorry.
Can you open it?
Yeah, it's still syncing, so it should now show up. There we go. Ah, there we go. So you can use this just to flip slides.
Okay. So for the last few years, I've been involved in applying spectral-induced polarization and electrical impedance tomography to the characterization of crop root systems. So it's a biological topic, quite challenging because, as it turns out, root systems exhibit only small polarization signatures. So, yeah, we were really happy when the next slide came. Yeah, when we put small root system in a small rhizotron container filled with tap water, you can see on in the upper figure or picture, and when we did multi-frequency electrical impedance measurements, and then applied a Debye decomposition to extract spectral parameters, we were able to really nicely image the extension of the root system using the polarization magnitude or chargeability. You can see on the left side in the lower left corner. Yeah, we were really able to delineate the root system extension. this was really nice. In addition, we observed really nice and systematic relaxation times derived from the Debye decomposition that you can see on the right side. And as already discussed, we only plot the relaxation times for regions where there's suitable chargeability to really exhibit a relaxation time or characteristic relaxation time. That is where we have a distinct shape of the spectral or the spectrum, the SLP spectrum. So we were really happy with the structural characterization, but it turned out that we can also, this is really dark. It turned out that we can also monitor and observe functional changes within root systems. So what you can probably not see here are two root systems in a container also filled with tap water. And tap water creates a nutrient-deprived environment. So basically, the roots or the plants were dying during the experiment. And then we observed those using EIT over the course of 1 week. If you now look just at the chargeability plot, if you look on the left side of the plot or the figure, you can see that the red blobs, the chargeability distribution of the root system, decreased steadily over the course of approximately, I think, 5 or 6 days. So we see that in accordance to the die-off or decay of the root system, the plant system, due to the nutrient deprivation, we also see decreasing chargeability signatures, which is a nice way to non-invasively monitor a crop root system, because usually we have to dig them out and do a destructive sampling of root system in order to get information about these. On the other side, just as in comparison, we decapitated the right plant to see what happens if we disturb the functions of the plant system. So if we basically stop any large-scale translocation of nutrient systems or nutrients or ions, and if we stop water flow in the plant. And it turned out the root can retain its polarization signature over quite longer time. At one point it will decompose, but that will take weeks. So we think this is pretty nice evidence that we are sensitive to physiological changes within root systems using SIP and EIT measurements. In addition, we also did really fast spectral measurements on root systems, and we were able to observe polarization signatures or changes in the polarization signatures over the diurnal cycle. So we see an increase in polarization of a root system in day or in nighttime hours, where roots store nutrients, where no or where physiological activity is reduced due to the missing light and due to missing photosynthesis. And we were also able to observe small but consistent changes in the relaxation times, which could indicate changes in the underlying length scales of the polarization processes. So this is really interesting stuff, but it's still quite challenging to apply this methodology in soil or substrates, because then we have the superposition of polarization signatures of the soil, of variable water contents and so on. So this is active research at the moment. We're also trying to, or basically we have been operating a field site for quite a few months where we do daily measurements, SIP or EIT measurements in the field here in Jülich. It's in the Transrego 32 project, but that's also still ongoing. So we really try to push the method on the field scale, where it will be really useful to have a non-invasive method for crop root research. And then, as a last-minute addition, we in the geophysics group here in Bonn have been thinking about putting together a Python library for importing, exporting, and working with electrical data from various systems, SLP, EIT, ERT, DC/IP measurements, because we think it would be really important to focus all these efforts that everybody is doing in writing their own importers, exporters, validating these algorithms. And yeah, I would be really interested, or is interested to know what you think about this. Are you interested in such projects? Would you be willing to contribute? Is this a matter for you? So, for example, what we are thinking about is putting together this library where you can not only import and export your data, but also manipulate your data. That is, apply data filters, plot your data. We're only talking about raw data. And directly have some kind of journal automatically created that basically describes all the actions you applied to the data, from the raw data to the exported data, which would really help in creating reproducible research. Yes, so this is more of a discussion opener, I hope. So it would be really interesting to know what you think about this. Okay, thank you very much.
Okay, I think this deserves a lot of discussion, but can we go back first?
Sure. Yeah.
Yeah, actually doesn't much matter in any place in there. What really intrigues me about this is the potential. I think I mentioned it before, but in British Columbia, the Vancouver area is really one of the top cranberry producers in North America, and produce just a lot of cranberries. And so they develop these cranberry fields, and there's a certain kind of soil structure that they put on, and then plants grow and things do really well. But then recently, over the last few years, there's been places that they have cranberry dieback, so the plants are just there's. I've had it explained. I cannot remember what was actually going on, but had all kinds of oxidation stuff that was. It seemed like, and if you look at the soil is different. So we went out there with just an EM instrument that kind of towed over in regions that had obvious dieback and had places that were looking good, and also did DC resistivity. But we never really found anything that was particularly diagnostic, but never really thought about using IP. And so you mentioned that signals are small. Do you have any sense if you're just kind of looking at one very kind of small root, if you had something that was just had a lot of roots there, that you might get a significant signal, any way of predicting?
We did some measurements a few years back in the field over the whole season and so on. So we're pretty sure there are signals, but it's really hard to get consistent signals and especially imaging results, because as soon as you go to field, you have these problems with electrode contacts, for example. You have flower horizon, which is really disturbed, so on. So I think it's more a technical issue, and on one side, but on the other side, in the field, you have lots of different variables. So water content is probably the major problem here. As soon as you have high clay contents, you get really huge signature changes with variable water content. So we will see what we can do about this. So it's challenging in the field. I think in the lab, it's pretty, we can do a lot of things in the lab, and I think it's a useful method in the lab today. but for the field, we need some more research.
Okay.
Yeah, maybe just to add on that, so this chargeability that we see here is sort of kind of figured out on the imaginary, basically imaged imaginary connectivity as well, over the frequency analysis. But if you look back at the data and so on, so in terms of phase, for instance, to give you maybe a number, it's all below 10 milliradians, right?
Yeah, 10, 15 millirads
of phase value.
The maximum. You can, if you put electrodes 10 centimeters next to a row of wheat plants or so, you can still see signatures in the field. We did this, but these were just spectroscopic measurements, so no imaging today. But this was probably due to electrode contacts and so on. So what we really would like to do is put the electrodes below the plow horizon. And we would have a stable environment over the whole growing season and stable electrode contacts, and this would probably help a lot.
I guess in this case history, I just had extracted a few images from Zong Engineering, who had shown that IP is a fairly robust indicator for waste dumps. But the one thing that they did have in there was green waste, which that was the first time I'd ever kind of seen that just green waste, trees, whatever, would actually have an IP response. Is that your sort of general feeling that research should have one?
One of our working hypotheses is that at every organic material we have biomembranes which are electrically charged and produce electrical double layers. So in theory, every more or less living biological matter should exhibit polarization signature. We know from bad experience that mold exhibits relatively large SiP signatures. So we had some of these rhizotrons contaminated with mold in one experiment and had really nice, consistent IP signatures over the whole growing time of the experiment, even before the plants actually started growing. So yes, I can imagine that this using IP for any kind of biological targets is possible. But on the other side, you have the superposition of all kinds of biological signatures. So it probably depends on the specific target area.
Oh, that's really interesting. Okay. Now we can go to the your last.
Yeah,
Talk about
do you
data.
want to pull up your last slide?
Ah, sure, sure.
So how far have you progressed along this line? Do you have something kind of mapped out in what you consider to be a prototype?
Yes, actually, I'm using the prototype on a daily basis. Every time I need an importer, I put it in there. I think it needs quite some polish to really show, for example, the journaling. I only experimented with it, so it's not really in a production state, I would say. So yes, but we have some importers, we have some exporters. The whole idea is to basically extract all these data or raw data processing tools out of these integrated processing pipelines and then provide a clear cut to, for example, inversion algorithms. So if you can export to data formats that can be read by, for example, by Gimli and BERT or our CATOMO code or REST2D-inf, there's no or there are no problems anymore in closed wall ecosystems and so on. And it would be really nice to also have one place for test data. So I think it's really important to validate and reevaluate all those importer functions because from experience, I know that sometimes you can go years without noticing any import errors that only slightly change your raw data and so on. So it would be nice if we had one place where everybody can contribute these tests and fixes. And yeah.
Do you have a repository started somewhere? Is it
I have. It's not published yet, but if you're interested, I can make it available.
That would be great. Yeah.
So one motivation is in particular with regard to error quantification. So actually, we haven't talked about that too much, although you mentioned it, Doug, that it's a very important component prior to inversion to think about that and quantify and get your inversion settings kind of properly. And so, and I guess that's every PhD student or whatever master student, bachelor student experiences that, then always going through the same thing, like with the inversion tools or whatever, it's very similar, but even before that, and then, okay, what type of, and then some of the analysis that came up in the last 10 years, in particular for ERT, like normal reciprocal analysis, like ranges of resistances, then fitting some models to get whatever quantitative, let's say, parameters describing like data errors, and all this is kind of not at all available in an easy way. So that is one aspect, for instance, and there's others.
Another important aspect would be that this would be, I think, a nice platform to start developing common data formats for all the electrical data. So, for example, I'm not aware of any data format for example, SIBP spectra. Everybody has something similar, but not quite the same. And I think this is, or gets important for long-term storage. For example, for all DFG projects, we are supposed to keep our data for at least 10 years. So we need documented data formats at one point. And this is quite a challenge yet. If we would have these tools to import and export the data formats, it would be no problem to really evolve on some data formats in there without losing any compatibility or usability in the process. So we could really iterate on it without problems. Yeah.
And one of the things that kind of crossed our minds about a year more ago when we were looking at this kimberlite deposit, we actually had some lab samples. We sent them to a lab to get them analyzed and get their SIP spectra, right? And then we realized that all of this stuff should ideally be archived in such a way that we know as much about the lab. Well, we know as much about the sample as we can from a geologic perspective, where when it was taken, all bits and pieces from that. But then also what analysis is done to that particular rock, when it was measurements were done. So even we might even want to know which instrument was being used, and there's a whole bunch of metadata that come with that. And then there's the initial raw data that come out of that. That is then subsequently, in the case we have, that is subsequently used as it's input into another program that kind of gets rid of really stuff that's happening at the low frequency, at the high frequency, and then you end up with this IP response. But sometimes you don't have 100% confidence that that processing in between was actually done correctly, or you might want to just go back and check it again and see if you could do something. So it's kind of what you've got here is kind of like a tip of an iceberg.
Exactly. Yes.
And the question is, how far one could go. Is there anything being done in the, let's say, in the German community with respect to archiving, laboratory work that has been acquired, so that you've got particular samples, what was done to it?
For one thing, it's an ongoing discussion, so people start thinking about how to store their data. But quite recently, I think last year, since last year, there's this initiative from Hannover, the LIAC Hannover, I think, they published these SIP database. It's basically a database where you can put in metadata and even the actual data of consolidated stones, or I'm not sure. So they're trying to build up an SIP database where you can search and even request the actual data. Yes, so it's active. I think the last time I checked, there were something like 300 spectra inserted in there. So it's kind of a national, no, it's an initiative until now restricted to Germany, I think. So, yes. So they're trying, working on it. I think there are a lot of things that need to be discussed. For example, how to include open data if somebody wants to just give their data away. This was, for example, last minute edition, as far as I know. So yes, there are things that are being done. Yes.
But I think in this case where you've obviously spent so much time and effort and you've kind of got a prototype, this would be an ideal time to, and certainly from our perspective, to just see, what's been done and try to get a sense of what your vision is, and then to merge that in with what we might think.
Yeah, but it would be really nice if you can do this. So yes.
I mean, in a way, it's sort of a similar discussion to Pi Gimli and synthetic,
Yes.
right? You've got two things out there, except at least in that case, both groups are advanced and you've done something. In this case here, we've talked about it and we recognize lots of needs, but we don't really haven't done anything, right? So the fact that you're actually well along the road here, both in terms of thinking about what is and about something that kind of works for you and is doing the job. That's a perfect place to say, okay, here's a strong map.
Yeah, I think we should discuss
what I think,
this.
we can just kind of discuss and see how to how to make it grow.
Yes.
That would be right.
I think so too. And another thing we've been discussing in the group here for the last year so is how to actually store our data. So the large projects, or for example, Jülich, the research center, they provide these large databases with the associated staff. But we as a small group don't have the resources to really set up large databases. And so we are looking for some kind of compromise between really collecting all the metadata and really making sure we have all the data and keeping it as small as possible and maintainable for small groups such as ours. And yes, we have also prototype based on just directories and text files for metadata, but the metadata is computer readable, so we are able to generate a database of the metadata to search it and so on, and then we just get directory paths to our data and so on. And
yeah,
yes.
And on that regard, so we're a small group as well with different sites. So we sort of joined the H+ network in France, where they do have more power to maintain the database, which is the database of sites, observatories, where you can have geophysics or logging, borehole, geotechnical tracing test. And so that's we basically feed in that database.
Okay.
With our different sites.
Will you use that as a primary data storage? Or do you have duplicate on your computers at home? Yeah. So
which is not that much organized, so I guess we'll practice and with time we'll probably merge towards that.
Okay. So do you have any solutions on how to, for example, take data with you when you're on a field trip? Because, for example, when we are in the Alps,
directly in real time.
You usually don't have a reliable internet connection there. So you need to have one way to synchronize parts of your database to a laptop and synchronize them back and so on. So I think this will be really important, at least for us, to really use the system and really commit to the system to be able to use it on a daily basis. So, yeah.
I mentioned this outside, but I think there's some interesting ideas in the open mining format.
Yeah, okay.
And a couple of the things that might come in handy in that case are, there's validation that is sort of built in from the ground up.
Okay.
And so being able to state what sort of assumptions you expect your data that you've read in to satisfy. So if you know things should be above 0 or something like that, you can actually have that checked as you read it in. And I believe that there are pieces that they've thought about in terms of the logging aspect of things. And because copying data sets over to different computers or different systems and checking checking that they are the same, that they are in sync, those sorts of validation pieces, I believe they've thought a lot about that.
Okay, yeah, that's really important, because I think checksums is a really important thing, and I think only few people are actually doing it. So really committing the data into some kind of database, or at least producing hashes and so on. And yeah, it goes quite down to the actual data storage, where you can discuss about file systems and so on. But I think we are still at an upper level of really figuring out what can work and what not.
Mm-hmm.
And how can we make sure to, for example, for the future, be able to convert to a database system if and when we have enough resources, or if it just becomes necessary.
Mm-hmm.
Yeah. And there are also quite a few problems with, for example, adding monitoring data. So if you just have a complete data set of a measurement, it's pretty simple to just put it in directory, write a README file or something like that, and capture probably 90% of the metadata you need. But if you have ongoing data, it becomes quite important to think about how to check the data, or make sure the data that you already have keeps consistent and so on. Yeah. So still ongoing.
That's great, Max.
Okay, thanks.
How many people are still wanting to present? There were 3?
Can I use my laptop? Because I have a movie and I'm not sure if it is working.
Sure, yeah, no problem. And you'd like to present as well?
Sure.
Perfect. Is there anybody else? Okay. Because what we could do, so it's 20 after 12. We could break for lunch and come back, or we could do one more. Do 2 after lunch?
Time for lunch.
Time for lunch? All right. Time for lunch. Very exciting. Very, very authoritative. Thanks.